And now I'm going to talk about what kind of crossover operators we can use. Yeah. Now, this slide just summarizes what crossover we are going to have. So the crossover, that is, we apply the crossover to both individuals as well as the strategy parameters, and then in general we have two approaches, that is local and global. Corresponding to local and global, we have two ways, that is the discrete, intermediate. When we talk about local, so that means local, we require each time we are going to generate two parents. These two parents are selected from the population. For example, we randomly picked two parents to form this selected parents to generate the offspring. In the global, we require that the number of selected parents should be greater than 2. Yeah. Okay. So, but when we say greater than 2, it should be less than or equal to mu. Otherwise, we will have some repeated parents in the group. Yeah. So which will be just wasting the computational power. Okay. And no matter what, each time, no matter whether local or the global method you are going to use, we will produce only one offspring each time. Yeah. Okay. So if we are going to look at the characteristic of the discrete recombination, that is, we are going to use the actual component from the parents. That means we have, for example, we have two parents. We are going to pick some element from these parents to form the element of the offspring. Yeah. So when we talk about the intermediate recombination, we are going to use the weighted average. Yeah. So that means we will not just simply pick some elements from the parent. We are going to use the information from the parents and then generate the offspring. Yeah. Okay. Let's go into detail about each method. So local, global, each with two ways. In total, we have 4, but actually we have 5 main types of recombination. It is mainly because the first one, that is, we could choose not to perform recombination. Yeah, when we do 1 plus 1 ES, and then so we do not need to do crossover. Yeah, but anyway, when we talk about local, discrete, crossover, and we will have this set of equation. This set of equation that we also call this is the uniform crossover as well. That means each time we are going to generate 2 parents, and then in each position of the vector, we are going to generate a random number. So based on the random number, we are going to choose the element from which parent. Yeah. Now this is an example. When you look at this example, it shows clearly what we are going to do. Assume that we have parent 1 and parent 2. We pick these 2 parents from a population. Yeah. And then now this is the first parent indicated by the blue color, and parent 2 red color. Now according to this equation, according to this condition, it in J, that is J position of the parent. Yeah. Again, to remind the notation, X11, the first one, it means that it is from the parent 1. The second one right here, it means that is the second position. Yeah. The first position of this this vector. Say when we talk about X23, 2 means that it is from parent 2. 3, it means that this element is at the 3rd position. Yeah. So when we do the crossover, we are going to look at the first position. In this first position, we have 2 options. The first option, the first thing we are going to do is to generate a random number. If it is less than 0.5, we are going to choose the element from parent 1. In this case, it means that we are going to choose X11, and then we switch to the next element. The next element, we are going to generate a random number. If it is more than 0.5, we are going to choose the element from parent 2, so and so. Yeah, we repeat this process for the following elements in the vector. The same applies to the sigma. So if you would like to reduce the computational complexity, you can use the same random number, yeah, R1, R2, R3. If you don't mind, and then you can regenerate this random number so that you can determine what sigmas to form the offspring from the parents. Yeah. Okay. Now we move on to the local intermediate method. So this is the weighted sum. Yeah. So this is the we can just find out that from these two sets of equation, they are the interpolation. If we are going to recall what we have done in the continuous genetic algorithm, this crossover that is very similar to the banding. Yeah. Okay. Look at this equation. Xj, that is the jth position of the offspring. Now again, when we do local rho, that is 2, it means that we are going to use 2 parents, and then each time we are going to generate one offspring. Yeah, so which involve parent 1 and parent 2, that is x1j, x2j. x1, that is the first parent, x2, that is the second parent, j means the jth position of the parents. R, that is a number in the range of 0 to 1, a randomly generated number. So R times x1j plus 1 minus R times x2j interpolation. Yeah. Okay. So an example right here. In the population, we randomly pick 2 parent 1, parent 2, parent 1 denoted by the blue color, parent 2 denoted by the red color. So according to this equation, the first thing we are going to do is just to generate a random number R. This random number R, that could be the same for all positions, or in each position you are going to generate a new random number. But anyway, I just use the same random number for all elements right here in the first, second, and the third position. Yeah, so to save computational just to reduce the computational complexity. Okay, this is the, when we look at the first element, R times x11 plus 1 minus R times x21, we use the information from both parents. Yeah, so the same applies to the sigma. Yeah. Okay, so repeat this process for the next position and then the third position, so and so. We come up with the one offspring. Yeah. And now the next, that is, we move on to the global. The global, it means that at least we should have rho greater than 2. It means that each time we are going to pick more than 2 parents from the population. Yeah. So global and the script. This formula, it looks a little bit complicated. Yeah, but anyway, we will have parent 1 x1, parent 2, parent 3, up to many parents. Yeah, but the number of parents, it should be less than mu. Yeah, so we will have this group of parents to generate one offspring. So this condition, it means that if we are going to each time in each position, that is the j position in the offspring, we are going to generate a random number. If it is less than 0.5, and then we will use the information from x1. Otherwise, this xsjj, it means that we are going to, if rj, that is more than 0.5, we are going to randomly pick one element from x1, 2, 3, and so on. If you still cannot follow, just look at this example. This example, I assume that rho, that is 3. That means in the population, I randomly pick 3 parents. Parent 1, parent 2, parent 3, red, green, red, blue, red, green. Yeah. Now, nx right here, that is, we have 3 elements for each parent. Yeah, so that is the number of decision variable of your cost function. And now we are going to look at this condition and then look at the j position, and then this j position, that is j equals 1, that is j equals 1, it means that that is the first position of the decision variable. So that is x11, x21, x31. Now I'm generating the first element, r1, that is 0.2. It is less than 0.5, and then I'm going to choose the element from x1. So this, we choose x11. Yeah, we choose x11 because x1, the first one, that is parent 1. So we are going to choose x11 as the first element of the offspring, and then we move on to the j position, that is j equals 2. So we move on to this position. So all j right here becomes 2. And then now I'm considering these 3 guys. Generate R2, this value in the second position. Now this time 0.8. That means it does not satisfy this condition. We are going to consider the otherwise case. So we are going to use this element j, that is 2. Yeah, so j, that is 2. So that means it indicates these 3 elements. So sj, it means we will have 3 options. 1, 2, 3. So it means that this sj, that is, we are going to randomly choose the value, the possibility that could be 1, 2, 3. Now I assume that s2, that is 3. We are going to pick the third element. Why do I pick the third element? Because I just randomly pick one from these 3 options. So I choose x32. And then we put this process, move to the next element, that is j equals 3. That is, in the third position, we have these 3 options. So generate R3 this time, that is 0.9, and then again it goes to the otherwise case. So otherwise case, so we need to find out what value of S3 should be. Yeah, so S3 we have 1, 2, 3 as well. So that means we are going to choose x1, x2, or 3. Randomly pick one. This time S3 equals 1. So x1, 3 is chosen as the third element of the offspring. And now when we apply the global discrete recombination, so we set a bias to the x1. Yeah, so that means x1 will have a high chance to be chosen. At least at this point 50% it has to be chosen. And then after that, if we are not going to choose x1 in the first place, in the next one we still have a chance to choose the first element. Yeah, the element from the first parent. Okay, so the same applies to sigma. Again, this time I just use the same R1, R2 as well as R3, S2, S3 as well. Yeah, so it is not a must, but for simplicity I just choose the same R right here. Okay, the next combination, that is global and intermediate rho greater than 2. Look at this equation. We have summation of all elements of x from the k parent in the j position, and then divided by rho. It means that we are going to take the fh value of all parents to form the offspring x in the j position. Yeah, take a look at this example. Rho, that is 3. That means we are going to randomly pick 3 elements of 3 individuals from the population as the parents to generate one offspring. Yeah, okay, blue, red, green for parent 1, parent 2, parent 3. And then now to implement this equation, that means in the first position, that is when j equals 1, so we are talking about 1, 1, 1, the first position, and then take the average, sum that up, and then divide it by 3. Because row this time, that is 3. We choose 3 parents. So the same applies to sigma. And then to move on to the next position, 2, 2, 2, and then the next position, 3, 3, 3, and so on. So this is the global intermediate recombination, or we call it crossover. Yeah.